In this problem, we're looking at a beam which is doubly cantilevered. That is, at both A and C, we have a wall. We have a line load which is constant in magnitude W naught between A and B. What we want to do is determine the vertical deflection of the beam at B. It also asks for angle of rotation, but let's just focus on the deflection. At the end, we'll talk about what you would have had to do to have also picked up the angle of rotation. I'm also going to ask that we ignore our shear effects. We're going to assume that those shear effects will be small for the cross sections that we have got. So as we look at this, if we want to use Castigliano, we have to have a load which is acting at the point where we want our deflection. To this end, I'm going to add a dummy force, PD. The dummy force is there so that we can use Castigliano to get the deflection at that point. We're going to start the problem out with equilibrium. I will write down the reactions here. I've got reactions, support reactions at A and C. I've got MA, I've got MC, and I've got this line load acting over this length there of A, so this is W naught A. And then I have the dummy force there of PD. For equilibrium, I will do a moment equation about A. I have the wall bending moment MA. I have the line load W naught A with the moment arm of A over 2 with a negative sign. I've got PD with the moment arm of A, it's a negative sign. I've got CY with a positive moment arm of L, and I have an MC like that. Summing forces in Y. I've got AY plus CY minus W naught A minus our dummy force there of PD. So as I look at this, I am faced with the reality that we have only two equations, and unfortunately we have four unknowns. So not only is the problem indeterminate, but it's indeterminate of order 2. The implications of the order 2 is that we need to choose two redundant reactions. That's our choice. Again, so that's a choice. I'm going to arbitrarily choose MA and AY. With that said, I will write our two equilibrium equations in a slightly different form, where I will write CY as a W naught A plus the dummy force minus AY. And I will take the moment equation and I will say that MC is equal to MA plus 1 half W naught A squared plus P sub dA minus CY, which was equal to W naught A plus PD minus AY times L. The reason I'm writing it in this way is that you see that the right hand side involves only the redundant reactions. Because at a later time we may need to use our equilibrium equations, which means we will need to substitute back in to our expressions here in order to get you the strain energy and just in terms of the redundant forces and of course any applied forces or dummy forces that we have got. So now I'm going to write down the strain energy. I'm going to say that the section 1 is going to be between A and B, and then section 2 is between B and C. So this is for section 1. What I will do is draw a free body diagram of the beam. I'm going to keep either the left or the right side. The cut is going to be somewhere between B and A. I'm going to keep the left side. And so what we've got here is AY. We've got MA. We have the shear force V1. We have the bending moment M1. And then we have a reaction, the applied force there of W naught X, where X is the position of our cut. I'm going to call that point there D. I think that's all we've got here. So what I will do is a moment about A, a summation of moments about A gives me minus MA, which is one of my redundant ones. I have W naught X. It has a moment arm of X over 2. It's got a negative SIGN sign in front. And let me change my mind here. I meant to say actually do my moments about D. So it's still at minus MA. We have W naught X times X over 2, which is now actually a plus. I have the M1, which is what I'm trying to find. And then I have the AY, which will have a negative moment with a moment arm of X. So let me count things up. I've got 1, 2, 3, 4 terms. That's good. So from this I get that the bending moment in section 1, M1, is equal to MA plus AYX minus 1/2 W naught X squared. So this is a very valuable term for us because this is what goes into our strain energy function there for section 1. For section 2, I make the cut now between B and C. In other words, in section 2, I can either keep the left side or the right side. I'm going to choose to keep the left side. You may keep the right if you want. The reactions I have here, AY and MA there on the left side. I've got the applied load resultant there, W naught A. I've got P sub D. I have got the M2. I've got shear force there of V2. And so from this FBD, I can do a summation of moments about, let me call that point where I made the cut H. I'm going to have minus MA. And again, this distance is X all the way over. So I got MA, I've got minus AYX. I've got W naught A. It's going to be a moment arm of X minus A over 2. I've got the dummy force there, PD. It's going to moment arm, a sign there of plus. It's going to have a moment arm of X minus A. You got 1, 2, 3, 4, 5 terms. I still need my M2. And so therefore from here I see that my bending moment over section 2 is equal to MA plus AYX This should hit a plus sign here. So that becomes a minus W naught A x minus A over 2 minus the dummy force PD x minus A, like that. Okay, so therefore the strain energy is what I get from 1 and what I get from 2. So U1 is going to be 1 over 2 EI integral from, since 1 goes from 0 to A, of M1 squared dx, and then 1 over 2 EI integral from A to L of M2 squared dx. Okay, where I have my expressions for M1 and M2 that you can see there on the screen. So let's think about what we want to find. We want to find the deflection at B. And we're going to use Castigliano on that. Just note this. We will say that the deflection at B will be equal to the partial of U with respect to our dummy force PD, provided that we set PD equal to a 0 when we get through. But you can see our strain energy is going to involve MA, AY, like that, which we do not know. We need to find MA and AY first. How do we find that? We will use Castigliano, and that says that if I take the partial of U with respect to one of my redundant reactions, AY, I'm going to have 1 over EI, 0 to A, of M1, partial M1 with respect to AY, dx. 1 over EI, integral from A to L of M2, partial M2 with respect to AY, dx. So what we have is partial of M1 with respect to AY. That is going to be simply an x. Partial of M2 with respect to AY is also x. The other equation is a 0. Partial U with respect to MA so that's 1 over EI, 0 to A, M1 partial M1 with respect to MA dx, 1 over EI, A to L, M2 partial M2 with respect to MA dx. So in this case, I need partial of M1 with respect to MA. Well, that is going to be a 1, as well as partial M2 with respect to MA is also a 1. One thing that I failed to write down, we've got the dummy force in there. Recall what we do. We introduce that, we do a differentiation, and then when we get through, we set it equal to a 0. So please note in these cases right here that once that differentiation is done, integration is done, we set PD equal to a 0 in each case. What this gives us, two equations in terms of two unknowns, MA and AY. These are two algebraic equations. We solve. Once we have that, Then we can now go back and get what we really wanted. So therefore now we can say that delta B is partial of U with respect to PD, as long as we set PD equal to a 0. And so what this ends up being is 1 over EI, integral from 0 to A of M1 partial M1 with respect to PD dx, plus 1 over EI A to L of M2 partial M2 with respect to PD. Again, we set PD equal to a 0. So what does partial M1 with respect to PD look? Partial M1 with respect to PD, that is a 0. Partial M2 with respect to PD is going to be a minus X minus A. Like that. So that will give us, now that we already know MA and we know AY, then from this, that will give us a number that we can represent for the deflection at B. Long question, and we didn't really do all the details here. But the important thing here is the process. We recognize right from the beginning we needed a dummy force there at B, because we're asked for a deflection there at B. So we kept that in. We recognize, secondly, that the problem was indeterminate by order 2, so we had to choose our redundant forces. We write our strain energy, U, in terms of those. We invoke Castigliano twice to get those reactions, and once we have those reactions, then we can finally get around to what we really want to do, and that's to find the deflection there at B. How would it differ if we instead were asked for this? If we're looking for the angle of rotation of the beam at B, in that case, we would have a bending moment, a couple MD, which would be a dummy moment. And we would do the same thing. We would carry that through. We would still be solving for AY and MA, but the final step then would be to use partial U with respect to MD, setting MD equal to a 0 to find the reaction, or I'm sorry, the rotation there at B.